Fill the kettle, flip the switch, and just listen. For the first minute, it builds. A low hum, then a hiss, then a full rolling roar that fills the whole kitchen. And then, right before it boils, something strange happens. It goes quiet. The roar drops away almost to nothing in the last few seconds before the switch clicks off. You have heard this 1,000 times. You have used that hush your whole life to mean one thing. It is ready. Pour now. But here is the part nobody tells you. The silence is not the boil. The silence comes first. The loudest moment your kettle ever makes is not the moment it boils. It is the moment just before. And once you understand why, you will never hear a kettle the same way again. So let us slow the whole thing down and listen properly. When you switch a kettle on, the heat does not arrive everywhere at once. It comes from one place, the metal element in the base. That base gets hot fast, while the water higher up is still cool. So for a while, you have a kettle full of cold water sitting on top of a plate of fierce heat. That gap, hot below and cool above, is the whole story. You can almost see it if you use a clear glass pot. Shimmering ribbons of hot water lifting off the base and sinking back down. The whole pot stirring itself, trying to even out a temperature difference it cannot close fast enough. Every single sound a kettle makes is a symptom of that struggle. Down on that hot base, the first thing you hear is not boiling at all. It is air. Cold tap water is full of dissolved air, the same way a fizzy drink is full of dissolved gas. Heat the water and that air can no longer stay dissolved, so it creeps out as tiny bubbles clinging to the bottom. That faint early hiss, the sound before the real noise, is just your water going flat. And notice where those bubbles appear. Not everywhere, but in the same few spots again and again. A scratch in the metal, a fleck of old scale, a rough patch on the base. A bubble needs a flaw to grow from, a tiny imperfection to cling to. A perfectly smooth, perfectly clean surface can actually make water harder to boil because a new bubble has nowhere to get a foothold. Your kettle roars along scratches you will never see. Then the real event begins. The base is now hot enough to boil the thin layer of water touching it. That water flashes into vapor and a bubble is born. A pocket of steam growing fast on the hot metal, but the water just above is still cold. And this is where it gets violent. The steam bubble breaks free, shoots up off the base, and rises into that cooler water. The cold water chills the vapor instantly. The steam inside turns back into liquid, and a bubble of steam that turns back into liquid does not gently shrink, it vanishes. The volume collapses to almost nothing in a fraction of a millisecond, and the surrounding water rushes in to fill the hole with nowhere to slow down. The inward rush slams shut. It is a tiny implosion. Each collapsing bubble is a little slap, a pinprick shockwave in the water. On its own, you would never hear it, but this is not happening once. On that hot base, thousands of bubbles are being born and imploding every single second, a chaotic machine gun of collapses. Layer thousands of those tiny slaps on top of each other, and you get exactly what you hear, that violent, rushing roar. So the roar of a kettle is not the sound of water boiling, it is the sound of steam being destroyed. Thousands of little deaths a second, each one a bubble that never made it to the top. And if that sounds like a strange, obscure bit of physics, it is not. It has a name, and it is one of the most powerful forces in engineering. It is called cavitation, the violent collapse of vapor bubbles in a liquid. And it is not gentle anywhere it shows up. On the propeller of a ship, spinning fast, the water pressure drops so low that it boils cold, forming vapor bubbles that then collapse against the metal blades. Those collapses are so sharp, they physically hammer the steel, pitting and chewing holes in solid metal propellers over time. Engineers spend fortunes trying to design cavitation away because a bubble collapsing is a genuinely destructive event. Ship designers, pump makers, even the people who build the giant valves inside a dam all fight the same quiet enemy, a bubble that forms, then vanishes, and lands like a hammer. It is nothing in ones, it is a roar in thousands. Nature found it first. The pistol shrimp, a creature the size of your finger, has one oversized claw it snaps shut so fast it creates a low-pressure bubble in the water. When that bubble collapses, it does two absurd things. It makes a bang loud enough to stun or kill its prey, one of the loudest sounds in the entire ocean. And for a few billionths of a second, the collapsing bubble reaches a temperature thousands of degrees hot, briefly riveling the surface of the sun in a flash of light too fast to see, a shrimp, making a tiny star by popping a bubble. That is the same family of events scaled down, happening thousands of times a second inside your kitchen kettle. The roar is a chorus of collapses. Sit with that for a moment. The next time your kitchen fills with that familiar rushing sound, you are not hearing water getting hot. You are hearing a storm of microscopic collapses. Each one a bubble that grew on the hot metal, tore free, raced up into the cold, and was crushed out of existence before it could reach the surface. The kettle is loud precisely because so many bubbles are failing. The noise is the sound of steam that did not make it. So now we can answer the real question: why does it go quiet? Because the water catches up. As the seconds pass, all that violent mixing drags heat up from the base and spreads it through the whole pot. The cool layer at the top slowly warms. And there comes a moment when the water near the top is no longer cold enough to kill the bubbles. Now, when a steam bubble breaks off the base and rises, it does not implode halfway up. The water around it is hot enough to let it survive. It travels all the way to the surface intact and breaks gently at the top. That is a real, full, rolling boil. And here is the beautiful part. Bubbles reaching the surface make almost no noise. There are no more violent collapses because nothing is collapsing anymore. The chorus of tiny implosions simply stops. The roar fades, the kettle goes quiet, not because it is finished, but because the fight is over. The bubbles finally won. They made it to the top. So read that sequence again because it is the exact opposite of what your ears told you. The loudest moment, the roar, is when the water is close to boiling but not there yet, and steam is being destroyed on the way up. The quiet moment, the hush, is when the water has actually reached a full boil and the steam survives. The sound you spent your whole life trusting to mean it is ready was actually the sound of not ready yet, and the silence you learned to ignore is the real signal. The hush is the kettle telling you it has arrived. This is not just a party trick. It is genuinely useful once you know it. If you want water for green tea or coffee, water that is hot but not boiled to death, the roar is your cue. That is the window in the loud phase before the hush. And if you want a true rolling boil, you do not need to stare at it or wait for the click. You can hear it. When the noise drops away, it is boiling. Your ears are a thermometer. People used this long before anyone could explain it. The old whistling stovetop kettle was really a clever trick built around this exact moment. It stayed silent all through the noisy collapse phase and only screamed once real steam, surviving steam, finally had enough pressure to pour through the spout. The whistle was tuned to arrive with the hush, not with the roar. Whole generations made their tea by reading a signal they never once had to think about. And there is a small, sad footnote for tea drinkers. Every second you let a kettle roar past the hush, you are boiling out the very last of the dissolved air, the stuff that left as those first tiny bubbles. Overboiled water is flat water, and flat water makes flatter tea. The kettle told you when to stop. You just had to signal backwards. There's even a name for the whole performance. People used to call it the singing of the kettle, and the pitch really does move as it heats, sliding upward as the collapses get busier and faster, then falling away as the bubbles start to survive. A kettle does not simply get louder and then quieter. It changes key. It sings up to the boil, and then it lets go. But the thing I keep coming back to is smaller than tea and bigger than kettles. You have stood in your kitchen thousands of times, half asleep, waiting for water, and the whole time a genuinely violent piece of physics was playing out in front of you. 1,000 tiny stars collapsing every second, and it was narrating itself to you out loud. You just did not have the words for it. The loudest part was the struggle. The quiet was the arrival. It was never noise. It was a bubble, being born on hot metal, racing up through the cold and dying before it could reach the light. Thousands of them. Every second, right there on your counter. So tonight, fill the kettle, flip the switch, and this time really listen. Wait for the roar, and then wait for the hush. That little drop into silence right at the end that is not the kettle finishing. That is the kettle telling you the truth it has been telling you your entire life. The silence is the signal. If you liked hearing the hidden physics in an ordinary sound, tell me in the comments what everyday noise you want taken apart next. I have a feeling your whole kitchen is talking to you.